Hi everybody, my name is Jimmy Carroll. I'm the Vice President of Operations at Tech B2B Marketing. I'm here at SPIE Photonics West 2024. I have the pleasure of being joined by Alex Fong and my colleague John Lewis. Alex, thanks so much for taking the time today.
Absolute pleasure.
So we're here today to talk about Hinalea Imaging. For those who don't know, could you give us a little background and let us know what you're most excited about right now?
Okay. Well, basically we have sort of a disruptive technology when it comes to hyperspectral imaging. So hyperspectral imaging has been around for quite some time. It's actually a spin-off of NASA's satellite programs. They were doing it with these things called the push-boom grating. Well, first they did it just with the different filter cameras, but then they went into using gratings. Basically, you can consider it a spectrometer pointed down and then capturing the spectra for a line of an image as it scans across the Earth in some sort of orbit. Well, fast forward to now, we've developed technology based on Fabry-Pérot variable etalons, and it's basically the most sort of versatile approach that exists. We can collect entire high-resolution ranges from throughout the, visible through the NIR, throughout the shortwave infrared, even up to the UV. We can cut down the number of bands. We can choose which bands we want to take. We can collect things like in a snapshot mode, so take a picture like a camera, or we can do it in real time where we stream out specific bands and collect out the spectra for an image for every pixel continuously. Mm-hmm. So this allows us to be used in all sorts of applications. We can monitor manufacturing processes or critical processes in real time. It can be used for security, surveillance, and defense applications to point out hazards. And then it can also be used in research, where you need extremely high, precision, high resolution, spectral and spatial information of an image or of a specimen.
A couple of terms that I've been confused about in the past, the difference between hyperspectral and multispectral. Can you talk a bit about that and clarify for us?
Sure. And you've given me the entree to give a nod to an IEEE committee I'm on. I'm sure my colleague Chris Durrell and his friends on that will be thrilled. There's a IEEE committee for the standardization of hyperspectral imaging terms and methods. And I think we've defined it essentially as multispectral being in the tens of bands, whereas hyperspectral is in the hundreds plus of bands. So it's really a resolution figure of merit. So at one point, if you're somewhere between like a 4 to 20, then you're multispectral. Once you go past like 20, 30, 40 or whatever, and you're into the hundreds, then you're hyperspectral.
Contiguous bands, right?
Yeah, basically. And that's a good point, because multispectral tends to be discrete, sort of separated bands. You've got typically channels. Yep. The way to think about it is channels versus this sort of more almost continuous, but it's also discrete, but almost continuous sort of range of values.
SWIR. I want to talk about SWIR, and that's something that can kind of go for, depending on who you ask, it might be multispectral, it might be hyperspectral. Right. It really seems to be, and this kind of speaks, I will back up for a second, is you mentioned it, but hyperspectral has gone from something really large and expensive in the lab to something that's like, I haven't seen a Hinalea camera up close, but I imagine they're not much larger than this, maybe smaller, and much less expensive. Right. Which has obviously led beyond. There's a number of other factors here, but this has led to increased adoption of hyperspectral, multispectral technologies on the factory floor in industrial automation, things like that. What are some ways that you're seeing SWIR used, right? Because for some reason it seems that SWIR is really gaining steam over the last couple of years, right?
Absolutely, and for good reason. So visible NIR is exactly what it sounds like. It's what your eye can see plus a little bit more beyond it. And there's a lot of information there. Certainly your eye cannot parse out these little spectral bands at 4 nanometer resolution, which is our resolution with that instrument. So these sort of fine gradations in between the wavelengths. But there's a lot of information outside of what our eyes can see. And shortwave infrared, that's where that takes us. So we can take a look at, for example, an array of white powders. We can distinguish between different pharmaceutical products. If you put down acetaminophen, which is commonly known as Tylenol, etc., aspirin, a couple of other sort of antibiotics, things like that. If you put them all down and you use a shortwave infrared camera equipped with some sort of spectral filter or etalon, as in our case, you can totally distinguish them very clearly. Their spectral profiles or signatures are quite different from one another. So using that plus add some machine learning to it, some classifiers, all of a sudden you can false color the, acetaminophen is different than the aspirin, is different from the baking soda, is different from the sugar, is different from the salt. All of it becomes completely detectable if it was a palette of colors. Where now this becomes useful, for example, we did a nice application with the Electric Power Research Institute where we used it in a test trial to see if we could identify corrosion, a type of a type of corrosion called boric acid corrosion from nuclear power reactor heads. So these small cracks occur in, under high pressure, and because boron is used as a moderator, that's what leaches out, and it causes this sort of white powder corrosion. But there's a lot of white powders in the nuclear power plant. There's gypsum and other, white things that are white. So if you can come up with some sort of way to differentiate between them, then you have an effective tool to detect these leaks. Well, we were able to do that, and that's online. We can, share the paper and everything. But not only were we able to do it like take a snapshot and do that with a lot of bands, we could do it with less bands, and to the point where we could put it on what's called a crawler, which is a type of rover, and in real time basically swivel the camera and look at that tube and see where the leaks are, and then highlight that using machine learning classifiers, highlight that in red.
Yeah, that's really interesting, right? When I think of some of this is maybe my own bias, but when I think of like industrial applications in SWIR and kind of non-visible imaging in general, one of the applications I think of is food and beverage, right? So would it be safe to say that if somebody is going to make a lentil soup at home, if they open up the lentils and there's no rocks in there, that there's a chance that a SWIR camera helped identify those rocks and sort them out and that kind of thing?
Yeah, that's a common ask, which is it's even got an acronym, FOD, foreign object detection. It's huge. We worked with a company that makes snack item, I can't really say, and the snack item involves potatoes. And when you're growing potatoes, apparently there's a lot of things that look like potatoes that get harvested, including golf balls and pieces of wood, etc. And so they were looking for a tool basically that could tell the golf ball from a peeled potato, from a piece of wood, and all these other things. And as it happens, fortunately, potatoes and golf balls and pieces of wood and rubber have different spectral signatures from one another. So it was easy to sort of highlight as red things that were not potato.
Yeah, so remember, next time you open a bag of snacks or a bag of lentils or something like this and there's nothing funny in there, then it's probably been seen by some sort of non-visible.
You don't see a Titleist sitting in there.
Yeah, you certainly don't want to bite into one of those.
Yeah, so I'm curious, we talked about food and beverage, pharmaceuticals. Are there other applications that are maybe up and coming where hyperspectral imaging may find application in the future?
Oh, absolutely. I mean, the big ones are all in ag and food production, and those are very exciting and important. I mean, I can't stress enough the impact. Obviously, the public has safety and health, but also just in terms of cost. Because if you have a situation where something that's contaminated with some sort of pathogen gets out, the current sort of turnaround time with most sort of assay or biochemical molecular technologies is like 72 hours or something like that. A lot of damage gets done in 72 hours. So we are working with, for example, the USDA on some projects to shorten that turnaround time. Conceivably, we want to hit something below the 8-hour mark. So if we can turn things around within, let's say, 4 hours, that saves a lot of lives, public health, and saves tremendous costs for manufacturers and for everybody involved in the food chain. So that's really exciting to us. The other side of it is also applications where we are detecting hazards. So right now we're in a project with the Department of Defense. We're looking at a way of detecting munitions, essentially, on the ground, explosives. And this is an older problem, actually, that's been around since probably, I think, the Iraq War, where people were interested in detecting IEDs. But now the technology, and in particular this machine learning or AI type of developments, combined with hyperspectral technology that's available, is making it possible for us to actually interpret the information on a timely basis. So what that means is kind of like that nuclear reactor head application. We can put this on a robot, drive it around, look at boxes, cars, things like that, and say, okay, that's probably safe, or okay, we better get everybody out of here. And I think what it comes down to, somebody once asked, hey, what do you sum up the sort of mission of Hinalea Imaging? And it's you know, it's human safety, really. It's quality of life. We're trying to make sure people are safe and healthy. And so that's a common thread of what we do.
I guess, sorry, John, go ahead.
I was just going to say, what differentiates their technology from, say, other hyperspectral imaging technologies that are out there?
I think it's flexibility. So the big one, you know, you see out there, the most ubiquitous hyperspectral imaging technologies are push broom. So these are basically, as I said before, it's really an adaptation of that technology that NASA pioneered for satellites. So you have a grating, a slit, it's a spectrometer. You tilt it on its side, you sweep it across field of view, and you get the image, very high resolution. But the time that it takes for you to sweep that area, things can change from one side to the next. The other technologies are basically digital versions of a filter wheel. So you're rotating around a filter wheel, getting the different bands. So there's time expended there, there's reliability issues if you make it solid state, so there's liquid crystal tunable filters or crystal optic tunable filters. One band at a time, not good transmission. The spin that we bring to it is we use an avalanche, 2 mirrors, that's how you select the wavelength, but we can transmit more than one band at a time. So we're collecting a lot of bands at any given point. So we can collect a lot of information very quickly with minimal sort of transmission loss. And you can choose which bands you want. You don't have to have all 300 bands across the entire range. And you get the entire image at that point.
So is there a maximum number of bands, an upper limit?
Well, basically it's proportional to the time that you can tolerate for acquiring that information. So, for example, we can collect about 10 bands per second. So that's where you call it hypercubes, right? So instead of frames, hypercubes per second. So 10 hypercubes per second is currently what we can do. If we increase the amount of light, shorten the exposure, we can probably collect even more. So these are sort of variables that you can play with. Whereas with other stuff, you know, you're kind of, your exposure determines, you know, whether or not you collect that line with the push broom, but you're going to collect all 300 bands, and it's going to take you that long to mechanically scan across the image. We don't have such limitations.
So that technology, we kind of touched on, from the application standpoint, we touched on some of the main ones, but are there any industries or applications that you see as being like hyperspectral imaging having a future in?
Sky's the limit, really. As we move outside of the visible NIR, which was a traditional sort of spectral range into the shortwave infrared, then we can go out into the midwave IR, long wave IR, and this is contingent on other technologies, detectors and everything, the image sensors, but we're also going to UV, so UV opens up a lot of new application areas in solid state, electronics, things like that. So yeah, there is any number of things that we have yet to see, that have yet to be explored. One of the joys, I think, of my career in photonics has been that we work with great customers, and people will, you know, often in other industries, people complain about their customers, but I don't. I love the fact that they come up with a new challenge for me every day, because the worst you can do is just say, I can't do that, but most of the time there's something you can do, and the fun is trying to figure out how you get there, and there's always something interesting. And we've discovered collectively at Hinalea all sorts of new ways to solve problems.
Very cool. Alex, or John for that matter, anything else we haven't talked about or anything else you haven't asked about that you want to cover today?
No, just check us out at hinalea.com, Hinalea.com, and that's it. We're based in Emeryville, California, just 15 minutes out of Berkeley.
Well, you heard it. If anyone has any questions for Alex specifically, they can reach out to us, and you can reach out to us via the podcast website, which is manufacturing-matters.com. Any general comments, questions, or even requests to come join the podcast, please feel free to reach out to us, and thanks for either listening or watching.